We are given a string s and we should rearrange the characters of s so that any two adjacent characters are not the same. For example, if our string s is AAB, then the answer would be ABA. As you can see, the first two adjacent characters are distinct and so are the following two. Another example, if our string is AAAB, then we have two possibilities. If we start with A, we know for sure that the next character is B, and then we are left with two A's at the end, so this is not a valid solution. And if we started with B, then we have three A's at the left, which is even worse. So for this example, there is no solution, and in such cases the problem asks us to return an empty string. I'm going to start by telling you that this is not an easy problem. Even when I thought about it, the solution didn't quickly come to my mind. But you know what to do when this happens. Whenever you don't have any idea of how to solve a question, you should think of an easier version of the same question. What can we make easier in this problem? Well, we can think about the number of unique characters in S and start with a number as small as possible. The easiest version of the problem would be when S consisted of only one unique character. And let's say that character is A. It doesn't really matter which one it is, right? If S consists of only one A, this is also the solution. If S consists of two A's, then we have no valid solution. We should print an empty string. Same if S has length 3, and so on and so forth. So this problem is actually pretty simple. We should just see what is the length of S. And if this length is 1, then we should return S, as it is the only case where we have a valid solution, and if not, we should return an empty string. Let's move on and make the problem a little bit more complicated. Let's say we have two unique characters in S, and these characters, of course, you can choose any two of them, but for simplicity, let's say they are A and B. The first observation you might have already made is that we don't actually care about the order of characters. We only care about their number of occurrences. For example, if S is AABB or ABAB or BAAB, what is really important is that we have two A's and two B's which we should arrange such that the condition is satisfied. Now that we made this observation, let's start with the simplest example possible. Let's say we have one A and one B. When we have two unique characters, there are actually only two possibilities of constructing a solution. We either start with A, and if so, we know for sure that the next character is B, and this is a valid solution. Or we can start with B, and if so, because we need a distinct character, we know for sure that the next character is A, and this is also a valid solution. Let's move on to a larger example. If we have two A's and two B's, again, there are also only two unique possibilities. We either start with A, then we know for sure that the next character is B, then we know for sure that the next character is A, and we know for sure that the next character is B, and this is a valid solution. The second possibility is if we start with B, and then we know for sure that the next character is A, then the next one is B, and then the next one is A again, and this is also a valid solution. Let's take one more larger example. If we have 3 A's and 3 B's, this is the same, right? First possibility, we start with an A, and then for sure we need a B, A, B, A, B, and this solution is valid. Or we start with a B, and then we need an A, B, A, B, A, and this is also valid. So, for two unique characters, when their number of occurrences is the same, we can actually go with any of these two solutions. This is simple, but what if the number of occurrences are different? For example, if we have two A's and one B. We have the first possibility, we start with an A, then we add a B, and then we add an A, and this is a valid solution. Or if we start with a B, then the next character is an A, and we are left with one extra A, which we should add to the end, and this solution is not valid. So from this example, we can already make another observation. If the number of occurrences is different, we can see that it is actually best to start with the most frequent character, in this example A. We have an assumption. Now what we need to do is to test it on other examples. If A is 3 and B is 1, is it best to start with A? Let's see. If we start with A, then we need a B, and then we are left with 2 A's. So this solution is not valid. But if we start with a B, then we will need 3 A's at the end, which is also not a valid solution. But you can argue that it's even worse than the first one. So our assumption holds true. There is no valid solution for this example, but starting with an A is actually best. Let's take another example, 2 A's and 3 B's. If we start with an A, we will have A, B, A, B, B, so this is not valid. But if we start with a B, we have B, A, B, A, B, which is valid, so our assumption still holds true. Now we know how to solve the problem for 2 unique characters. If the absolute difference of their number of occurrences is greater than 1, then we will have no solution. But if it is at most 1, then we will start with the most frequent character, and then, of course, the solution is going to construct by itself. The next step is to solve the problem for 3 unique characters. Let's take an example. 3 A's, 2 B's, and 2 C's. Is our assumption correct for this example? Well, we should start with an A and decrement its number of occurrences to keep track of them. And then we can add a B or a C. It doesn't really matter which one. Let's say we added a B, decrement its number of occurrences. Now we will add a C, decrement its number of occurrences, and we can do the same again, right? A, B, and C, decrement the number of occurrences, and in the end add another A, and we have a valid solution. So, from this example, we might already have an idea of how to solve the general problem, or at least I did when I've solved this example. I was thinking, isn't it best to continuously add the characters in decreasing order of their number of occurrences? In this example, the characters sorted decreasingly by their number of occurrences are A with 3 occurrences, B with 2 of them, C with 2 of them. And what did I do? I have continuously added them in this exact order. A, B, C, A, B, C, A, and then I was left with no characters. Now we have another hypothesis, and of course, we have to test it on other examples. Can you think of a counterexample where this hypothesis fails? Well, I can. Let's take this one. If A occurs 3 times, B 1 time, and C 1 time, what should we do? A, B, C. Then I'm left with 2 A's, no B's, and no C's, so I'm forced to add 2 A's at the end, which is not a valid solution. So our algorithm finishes, and it returns the empty string, as we haven't found a valid solution. Okay, that's not necessarily a problem. Maybe this example doesn't have a valid solution at all, so our hypothesis still holds true. Well, it does. What we can do is still start with an A, which is the most frequent character. Then add a B or a C, it doesn't really matter as their number of occurrences is the same. Let's say we add a B. And now the problem with our algorithm was that it added a C and then we were left with 2 A's, which gave us a bad solution. But if you look at the number of occurrences, now we are basically left with the problem with 2 unique characters, which are A with 2 numbers of occurrences and C with 1 number of occurrences. And we know from the first observation that starting with the most frequent character is best. So maybe adding an A is best here. Then we will add the C and then another A, and we have a valid solution. This is very interesting. We have just seen an example where the first observation fails, but we still have a valid solution which we can construct using the first observation, which still holds true. So instead of continuously adding the characters in decreasing order of their number of occurrences, this is not correct anymore. What we should do is actually use the first observation and continuously add the most frequent character at each moment of time. But this approach will also have a little problem. Let's recap the example. Initially, the most frequent character was A, so we added an A. Now, the most frequent character is still an A. But now, we shouldn't add another A, because the last added character was an A, and this will provide a bad solution. What we should do instead is, after adding the first A, we know now that this is the last added character, so we should put it on hold. We should say, okay, continue with the most frequent character which is available. So in this example, we put A on hold and now we have B and C. Which is the most frequent? Well, both of them are. Let's say we are using a C. We add a C and now the C is on hold. We can't use it at the next step and we have to see which one of A or B is the most frequent character. And it's A. We use an A, decrement its number of occurrences, and now put A on hold. What is the most frequent character between B and C? Well, we have no C's left, so it's B. Decrement its frequency and put B on hold. What's the most frequent available character? Well, the only one which is left is A, so this is going to be our solution. We put A on hold, but of course we see that we have no characters left, and indeed we have found a valid solution. And this is it. Honestly, after I came up with this solution, I've taken 5 or 6 more examples to really validate my hypothesis, and it worked for those. It would take me another 10 minutes to go through more examples, but this is what you should always do. I always suggest that you start with easier versions of the problem, and for that easier versions, take the easiest examples first and make some observations. Each time you made an observation, just write it and take 3-4 more examples to see if it's really valid. In our case, if we didn't do that, we will now be writing code for that solution, which we actually proved that it's not correct. So, let's recap the solution again. First of all, we should count the number of occurrences of each letter, and we already know how to do this. We will use a hash map, and let's name it frequency. Then, our algorithm will perform exactly length of S steps, each one for each character that we will add into the solution. For each of these steps, we can iterate through frequency and find C, the most frequent available character. Then, we will add C to our solution string and we will decrement the frequency of C. And this is the most trivial approach. Now let's see, what is the time complexity? Counting the number of occurrences of each letter means traversing the string S and incrementing the frequencies. So if the length of S is denoted by n, this takes big O of n time. Then the for loop performs n steps, and for each step we should iterate through the frequency, which has a size of sigma. Just a reminder, we use sigma to denote the number of characters in the alphabet, so sigma is 26. And then of course, appending C to the solution and decrementing its frequency takes constant time. So for each of the n iterations in the for loop, we make big O of sigma, which means the time complexity is big O of n times sigma. What about the space complexity? The only extra space that we use is the hash map, which is of size sigma, so the extra space is big O of sigma. This is actually not that slow, because as I said, sigma is 26, which is a fairly small constant. But in a Mang interview, for example, the interviewer will surely ask you for a faster solution. In this problem, we are dealing with a string of characters, but it also can be easily extended to an array of integers. If we were given an array of integers, which let's say are up to 1 million, so that sigma is actually 1 million, then yeah, for sure you will need a faster solution. The optimal solution is actually big O of n times log of sigma. And what we are going to optimize is finding the most frequent available character, which takes now big O of sigma. We will optimize this to big O of log of sigma. Well, this is actually not that unfamiliar. We have a collection, in our case, the characters along with the frequencies. At each step, we should find the greatest frequency and then update that greatest frequency to its decremented version. So basically, we need to get the greatest element from a collection, remove that element and update with a new value. Yes, this is the max heap. Let's see how the solution with max heap looks like. The first step is the same because we need that hashmap frequency. But now we will use a max heap, and let's name it simply max heap, which consists of pairs that look like this. The frequency of the character C along with the character C for every available character C. And using pairs in this max heap is necessary. Think about it. If we only stored characters C, then we don't have a comparison criteria. The max heap would always take the greatest alphabetically character, which is not correct. If we stored only the frequencies, this is a little better. We will get the greatest frequency, but that's it. We will only know this number. We won't know also the character which that frequency corresponds to. So we won't know what to append into our solution. So this is why we use pairs, and some coding languages like Python or C++ will automatically compare these pairs, first by the first value, so first by the frequency, and then, in case of equality, by the second value in the pair, which is the character. Which doesn't really matter if you think about it. If we have two characters with the same frequency, we can take any of them into the solution, and that's fine, as we have seen in the examples. Other languages don't automatically do this. For example, if your language is JavaScript, you are going to write a comparison function that compares two pairs by their first value decreasingly. Because initially our solution is empty, so we don't have a last added character, which means that all the characters in S are available, we will initialize this max heap with every pair, frequency of C and C, for every character C in the hashmap. In order to solve the problem of taking into account only the available characters, we will use a variable prev, which will store the last added character to the solution along with its frequency. And you will see how this works in a minute. But basically, the max heap will not contain prev. It will contain only the available characters, and only after adding to solution the most frequent available character, then we will insert prev into our max heap, as now it became available. Prev is initially equal to none, as we don't have any character added to the solution. And then we do the same, we perform a total of the length of S steps. And for each step, we have to find the character which we should append to the solution. And that character will be taken out of the max heap. But the question is, what if the max heap is empty? Then we should return the empty string. This means that we don't have any characters which have a frequency still greater than 0 and are different than prev. However, if the max heap is not empty, then we will extract the greatest pair and store these values using the variables counter and character. Then we will append character to the answer. And now we should decrement counter and set prev to this counter and character, as now this is the last added character to the solution. But if we do this now, we will basically forget a very important step, which is that we had a previous character which was unavailable, but now will become available, and we should insert it into our max heap. And the problem is that if we execute this last line of code before inserting prev into the max heap, we will basically lose its original value. So we should first insert the original prev into the max heap, and then we should update it with the new one. We will check if previous is not null, and if so, we will insert it into the max heap. Then, after we decrement the counter, we should also check if the counter is not 0, because we don't want to insert into the max heap characters which are no longer available. Otherwise, if counter is 0, then we will set previous to null, to denote that at the next step we don't have anything to insert into the max heap. And this is it. After the for loop terminates, what we should do is return the answer. If this is our string s, we will first create the hash map with the frequencies, then we will initialize max heap with all the pairs, and then we initialize prev with null. We enter the for loop, step is 0. Is max heap empty? No, it's not. So we proceed, and we extract the pair free and a from the max heap, so counter is free and character is a. We append character to the answer, and then we check, is prev not null? No, it's not. We decrement counter. Counter is greater than 0, so prev becomes the pair 2 and a, and we continue. Step is 1. Is the heap empty? No, it's not. We continue and extract. Counter is 1, the character is b. We append b to the solution. We check if previous is not null, and now it's not. So we will insert the pair 2a into max heap. We decrement counter. Is counter greater than 0? No, it's not. So prev becomes null. Next step. Is max heap not empty? No, it's not. Extract the greatest pair, which is 2a. Append a to the solution. Is previous not null? No, it's not. Decrement counter. Is counter greater than 0? Yes, it is. So previous becomes 1 and a. And we continue. Heap is not empty. We extract the pair 1c from the max heap. We append c to the solution. Is previous not null? Yes, so we insert the pair 1a to the max heap. We decrement counter. Counter is now 0, so prev becomes null, and we continue. Is max heap empty? No, it's not. We extract the pair 1a. We append a to the solution. Previous is null, so we do nothing. We decrement counter. Counter is not greater than 0, so prev is still null. And this was the last step of the for loop, and indeed, our solution is correct. Now let's analyze the time and space complexities of our algorithm. First of all, we have the for loop, which performs a total of n steps. Then, inside the for loop, we extract the maximum element from the max heap. And because for each letter of the alphabet there is at most one pair which lies in the max heap, the size of the max heap is sigma, and this operation is big O of log of sigma. So is inserting an element. So the time complexity of this piece of code is big O of n log sigma. Now let's get back to the steps prior to this code and see what is the time complexity there. Counting the number of occurrences of each letter is big O of n, because we have to traverse the whole string. And initializing the max heap with every pair corresponding to a letter is big O of sigma. So the final time complexity is big O of n log sigma. And again, because the size of our heap is at most sigma, the extra space used by our algorithm is big O of sigma.